Right, folks. Welcome to the last and final of the Ring Zero Return to Workshops 2022. This is the final of the set of workshops. Today's workshop is going to be titled Introduction to Cryptography by Dr. Jean-Philippe Aumasson. First, I want to welcome you all. My name is Aumasson. I am the founder and organizer of Ring Zero Training and also co-instructor. Ring Zero workshops are always our gift to the cybersecurity community. Every season before a main event, we conduct a set of workshops. Our intention is to showcase the excellence that our instructors bring to the table and feature a little bit of their training to the audience at large, so you folks get a flavor of what we all do and what we all teach about. JP is an instructor with us. He's been teaching stuff about advanced cryptography since a number of years. JP is teaching along with his colleague Filip Jovanovic about cryptography fundamentals and advanced cryptography ciphers at Return to Exploit, which is a virtual training event happening in February. Let me also introduce JP. He is a good friend. He's a very well-known security researcher. He is a legend-ish in the name of, he's a legend in the area of cryptography. He is the co-inventor of the Blake hash and an author of 2 excellent books on cryptography. With this introduction, I want to turn over the workshop to JP.
Well, thank you, Samir, for this presentation. I'm blushing. So very happy to be here. Thank you for having me again. And very happy to be part in this of this series of training. I think Ring Zero is the best you can find in terms of content. And as a speaker, as a trainer, it's also the best experience I had in terms of organization, in terms of content, in terms of setup. So very cool to do this again. So let me try and do what's usually the most challenging in this exercise, namely sharing my screen. So what we're going to do today, we have only so much time, a bit more than 1 hour. And I usually give this training over 4 days. So I don't want to cover all the topics in such a small time window. So what I did is I picked the topics which are maybe the most accessible. So the most introductory topics, the one that we present on the first day, namely randomness, public key, and symmetric key cryptography. And I will present these 3 sessions, but in a shortened way compared to what we usually give. So I will share fewer details than what you would have in the actual training session. And also to give you some flavor of the more advanced content, I will also talk about post-quantum cryptography, quantum computing, and even ZK zero-knowledge proofs. So that's another league, another level compared to the basic stuff, but hopefully you will learn some insights from that. So let me start. And at the end of the session, I will be happy to take questions that you may have. I'm not sure I can see the chat window of Zoom in case you have questions. But I will leave some time after each presentation to hear your questions. Okay, so let me minimize the Zoom thing. And there we go. So you might be surprised to see that I don't start with encryption or decryption or whatnot, but with randomness. Why? So randomness is the most important thing in crypto. So let me put. If you don't have randomness, you have no cryptography at all. you have no encryption, you have no signatures, you have no key agreement, you have no secure channels, you have nothing. Because you can find randomness in all the cryptographic components, or what we call primitives in crypto, be it in encryption, in key generation, in public key signatures, in the key agreement protocol. So every time you connect to an HTTPS website, you use encryption, you use key agreement, you use public key cryptography. And even more in the more advanced topics such as ZK, zero knowledge proofs, you have a lot of randomness being used. So what does it mean to be random? If you look at this series of bits, there's 30 bits. We have 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0. Well, that looks pretty random, doesn't it? You don't see any pattern. It looks like someone just picked these numbers arbitrarily. And if you pick a random, a purely random string of 30 bits, you have a chance to get this series of bits. The chance is 1/2 to the power 30, or 1 divided by 2 to the power 30 is the same. So you have very small chance of hitting this number. Now, let's say you pick another random number and you obtain this one, you obtain 0, 0, 0, 0. You might say, oh, well, something must be broken because it doesn't look random at all. Look, there's 0 and 0 and 0 again, another 0. So it's not random, but it has exactly the same probability to be chosen as the previous one. So mathematically, this is not less random than the other one. When we say this doesn't look random, is because we don't see patterns in this one, in the first one. Whereas with 0, we see the pattern. We see that obviously it's only 0. There's something remarkable, something unusual, something that strikes us, in terms of pattern detection. That's how our brain works. So where I want to go is that it makes little sense to say, oh, this is a random number, or this is a non-random number. Instead, there's only methods to produce random numbers. So methods meaning programs, mechanisms, techniques. But if you look at the number here, the number is itself may have been randomly produced, but its value is not something that can be random or not random. So later, when we say random number, what we actually mean is a number that was produced using a randomized technique. So what does it mean to be random? What does it mean to be random or pseudo-random or truly random? So there's different components in the random generator that you have in a computer, for example. So the first component you might have is what is sometimes called the true random generator, or TRNG for true random number generator. So it's something that just gathers information from the environment. It might be what keys you're pressing on the keyboard, the movements of your mouse. It can be the temperature of the room. It can be some noise. It can be sensors on your CPU. So something that comes from outside of the system. It can be the network activity, the logs of your system. So all this stuff that is unpredictable in practice. And you use this information to aggregate all this data in the form of, for example, big tables of data. And it's what is sometimes called the entropy or the uncertainty that comes from the environment. So you look at the Linux or the Windows operating systems, there are components that will gather information from what you're doing on the computer and how your computer is working. And also in your CPU, in your chip, there are some, kind of physical mechanism that will also create some kind of randomness. So that's one thing. Then you have this big pool of entropy of data that is, quite messy and predictable. And then as a user, you say, I want some randomness. So you will use something that we call a deterministic random bit generator. So this sounds like an oxymoron because random should be the opposite of deterministic. Random should be non-deterministic. So what this means is that you start from an initial value, you start from bits that are actually truly random, so to speak, and you generate from this starting value, you generate more numbers, you generate more data in a deterministic way, and this data will be usable by the applications. And the difference is that when you, for example, you collect data from the temperature of the room, the temperature of your CPU, it might be biased statistically because you can more or less predict the range of the temperature of a CPU, for example. But what we want is data bits which are, statistically random. For example, if you take a value 0 or 1, you want it to be 0 half of the time and 1 the other half of the time. And the third bullet is a pseudo-random generator. So it usually refers to the combination of these two components. So the true generator, the thing that collects information from the environment, and the deterministic part, which extracts bits from the random data. So you will see different terminology if you look on different resources, different papers, but that's the one I like to follow. And that's the one that also I put in my book and that many people use. Another important point is that computers give you random bits, so random zeros and ones. But in the real world, you usually want more than this. Maybe you want random images, you want random numbers, you want random cards. So you have to convert the random bits in random stuff that you need to generate. So usually converting bits into numbers is relatively simple, but if you go to something a bit more structured, it can get more complicated and error prone. For example, you want to generate a random word, random letters. You have to pay attention to a lot of details to get it right. Now the word entropy, which is usually intimidating for a good reason. It sounds maybe, it reminds me of my classes of thermodynamics at school, and I have some PTSD about this. But entropy in the context of crypto is much simpler than entropy from physics. So we only talk of what we call informational entropy. So it's just a notion to measure the amount of uncertainty in some random process. So let's say you have a secret key of 128 bits. So each of the bits is completely unknown. So the first one can be 0 or 1 with the same probability. So it means we have 1 bit of entropy, 1 bit of uncertainty. And since we have 128 of these bits, we have entropy of 128. So mathematically, computing the entropy is not that trivial. It means taking the logarithm in base 2 of the number of choices you have. And a big difference is that the entropy is not always the size of the key, is not always the size of the secret. More generally, is the logarithm of the number of acceptable choices. Because in some crypto systems, not all the keys of a given size might be acceptable keys. So if you look at RSA or some other complex crypto systems, the entropy is not always the size of the key. So what is important is when you generate random values, the entropy of your pseudo-random generator should be at least the size of the key. And another important point is that the entropy of the key is not always equal to the security level. So let's take the case of the cryptography we use, they used to connect to this call, to the Zoom call. So under the hood, it's using something called elliptic curves. With an elliptic curve, where the secret key has 256 bits. But the security level is only 128, which is good enough, but it's not the same as the key size. Okay, that's all very, very abstract. So let's go back to something more concrete. I don't know if you were born in 1996, but the first popular internet browser was called Netscape. And the people who made it are now very rich. They have a famous VC fund. And in Netscape, there was a pseudo-random generator, which looked a bit like this. And the question we want to answer when looking at this code is, how secure is it? And specifically, how much entropy, how much uncertainty do you have in the system? So the important part is the first function, RNG create context. I just give you, say, 30 seconds to look at this. So what is this doing? We see seconds, microseconds, time of day. Okay, so it takes the time of day in seconds and microseconds. There's what, 60 seconds in a minute? So we have at most 60 possible seconds. How many microseconds do we have in a second? So we have 1,000 milliseconds. So we have 1 million microseconds. Okay. So here we have 1 million times 60. We have 60 million possible values. And then the PID, so the process identifier, the PPID, each of these values on a Linux system is 16 bits. And then what do we do? A, B. So we just transform these values. So the uncertainty, the entropy, or the random generator here just takes data from the time of day and the PID. Now we can try to reason how much entropy is that. And so people did this exercise. So they did the analysis that we just did. They looked at the variables, which are not predictable. And they also asked the question, can we predict these values? So let's say if you're on the same machine, and if you know approximately when the system was running, then you can guess the PID and the PPID. You can guess the process identifier by just using a simple command on the machine. And the microsecond is the hardest one to guess. So then you have one chance in a million to get it right. But now let's say you don't know anything about the PID, the PPID, you're not on the same machine. And you can try to quantify the entropy. And I skip the details, but the conclusion that you can see here is that you get at most 47 bits of entropy of randomness, which is way too low to give you good security. In practice, you want at least 80 bits in most cases. So there are some corner cases, but at least 80 and ideally at least 128. So that was in 1996. Okay. So the upshot here is that you should pay attention to where you get your entropy from and try to quantify how much entropy you get. So this is the Linux kernel PRNG. I put 2 updates because there has been a few developments this year, but the way it works is basically what I described before. So it gathers information from your system and from what a human person is doing with the system. Because, you know, the most unpredictable stuff on the planet is human behavior. You know, we all have example of these people doing the opposite of what we expect them to do. So they're very good, you know, random generators. And the blue thing is the entropy pool is this big table which gathers all the information about what humans are doing. And then you have the red part and the green part. I will explain the details later. It's where the DRBG or deterministic generator comes into play, where it extracts data from the blue table. So this year, the Linux people, they did a few changes. They modified the hash function SHA-1 with Blake2S. This function is used for mixing the entropy pool. And also the deterministic random generator is now using ChaCha. It's been using it for a while. And ChaCha is a stream cipher. So it's something that is usually used for encryption, but you can also use it to generate randomness. Okay. So the way you can use this generator is to use its interface, which is a file, a device file called /dev/random on a Linux system. And you just read from this file like if you are reading a text file, except that it's slightly different. But what you see here is not the right way to do it. You should not do it like this. It's too risky. There's also something funny in the Linux system. There's a file that gives you the entropy in the system, but this is completely not reliable. And if you update it to the latest Linux kernel, it's not working that way anymore. But historically, there was this entropy estimator, which was doing something a bit stupid. It was thinking that every time you read from the system, every time you obtain random bits, then this was considering that the entropy was reduced, which is not a very correct thing to do, mathematically speaking. So there's been two interfaces to this PRNG in Linux, dev/random and dev/urandom. And historically, the dev/random was blocking. So blocking meaning that it stops spitting out random bits. It would block if it believes there is not enough entropy. So initially, it was designed as a security feature to prevent you from having insecure bytes. But what I've seen many times is that it kind of backfired, because if you expect random bytes and you don't get anything at all, well, sometimes it's better to have suboptimal randomness than no randomness at all. But now, since a few months, dev/urandom is always safe, and dev/urandom will not block as it used to. And also the entropy estimator will return at most 256 bits, and the entropy will not go down if you read from the PRNG. Okay. So if you write C code on Linux, the best thing to do is to call the system call get_random, which is saving you a lot of hassle and a lot of details if you need random numbers. So on Windows, there's something equivalent called bcrypt_gen_random. It's also the interface to the Windows PRNG, which works very differently, but which is also pretty fine in terms of security. So what's most important is if you deal with cryptography with security applications, you should use a cryptographically safe random generator and not an unsafe one. So it sounds obvious, but historically there's been a lot of insecure random generators used because of two reasons. The first one is that many systems integrated by default a non-cryptographic PRNG. And the second reason is also the documentation is not always clear when you're a developer. So if you're, for example, writing code in C++, there are these two functions that I mentioned. There's the OpenSSL library, which gives you an interface with a pretty good, pretty safe PRNG. In other programming languages, now you have most of the time as part of the system, a cryptographically safe randomness module. That's an example in the Go language. So you might ask, what's the difference between the bad and the good here? So it's quite simple. The definition of security for randomness is the following. So let's say you're generating random bits and you can observe, let's say, half of it. And you want to determine the other half. Well, if your generator is cryptographically safe, then you will not be able to determine the other bits from the ones you know. Whereas if you have a non-cryptographic one, which will be very simple and maybe also very fast, then the bits you know will tell you enough information to determine the other bits. So the bits that come after or the ones that came before. That's another example in MediaWiki. It's the software that is behind Wikipedia, for example, and also many wiki-like applications. So this bug was in 2012. I remember I put it in the first version of the training, which I did in 2013. So here, this function is generating a random password. So it's used, for example, when you do a password reset, you forgot your password, and you get a random temporary password. So I don't know if you can see the problem in this, but it's at the line minus 2, the line in the for loop at the end. Here we have a function called mt_rand. I don't know if you have any idea what this could do. So if you don't know, it's hard to guess, but MT, so the letters MT stand for Mersenne Twister. It's a funny name, but it's what's not funny is that it's completely insecure. It's a random generator that was designed for statistical simulations, but totally not for security and totally not for crypto. So here, if you pick a random password using this function, then an attacker that just sees a handful of passwords, they will be able to determine the state of the system, which means they will also be able to determine the passwords sent to other people. So there's a paper that describes all the details. And if you look really under the hood, you will see that the entropy is only 32 bits, which is ridiculously low for this kind of application. Okay. Now, the last part, how can you make sure that a pseudo-random generator is secure? Well, the bad news is that you cannot. You can only prove that it's not secure. And ironically, the reason it is so is because of how security is defined. You cannot prove that something is secure because otherwise it would mean proving that there is no attack. And proving a negative is always difficult. You can only prove that it's broken by proving that an attack exists. And one example of a simple attack is just if you find a statistical bias. If you have more ones than zeros, or if you have, let's say, more patterns of a certain type than expected. Let's say you look at patterns of 4 bits, and it might be that the pattern 0101 is more common than the pattern 1011, for instance. So there's a bunch of statistical tests which will do all sort of statistical, non-trivial statistics, and will give you an indicator of how good your output is likely to be. But you cannot prove that a stream of random bytes is secure just by looking at it. At least you need to look at the code at what is, under the hood. So if you have any question, please ask them now about this part. Meanwhile, I will switch to the next deck. Okay, so let me continue with now some real crypto, some actual encryption, and the easiest type of encryption, the symmetric one, as opposed to asymmetric or public key. So what we want to do here is encrypt stuff. What does that mean? Of course, it means turning messages into encrypted messages. So encrypted means secret. So secret means that it has the property of confidentiality. That's how the words we use in crypto. But to some extent, we also want to protect the integrity of data. So having some assurance, some guarantee that the data hasn't been modified. And authenticity, meaning that if I receive a message from my friend, I want to make sure it really comes from them and not from someone else. There's another notion, non-repudiation, which cannot be achieved with symmetric encryption, with symmetric crypto, and only with asymmetric. So that's what we've seen just before, the deterministic random bit generators, the RBG. So it's super stupid and simple. You start from a small value that we call the seed, and you generate a big value, potentially huge, can be gigabytes of data, terabytes, if you'd like. And that's what the DRBG does. It expands a very small piece of data, which can be just 128 bits or 32 bytes or slightly bit more. And that's it. And the security definition is what I mentioned before. If you know part of B, you should not be able to determine the rest. Otherwise, it's broken. Even if you know all the bits but one, then all the bits that you know shouldn't give you any hint on whether the other bit is more likely to be 1 or 0. So that sounds magic, but that's how crypto often sounds like. So now, what would be the inverse of a DRBG? The inverse, I mean something that takes data of any size, potentially very big, and that creates something very small of constant size. So as some of you may have guessed, we're talking about hash functions, which is my favorite topic. Also because it's the simplest. Well, from my perspective, because you just take any large piece of data and you scramble the bits around, you combine all the bits into something small, so you really compress the data. And the main guarantee that you want from a security perspective is that finding two outputs that are identical for two different inputs should be hard. So that's what we call a collision. A collision is two different messages that hash to the same value. And also, we also want that the function be hard to invert. So that's why we also call it one-way function, meaning that if you have a digest, H, it should be practically impossible to find a message that maps to this value. But of course, there will inevitably exist such values because I don't know if you're familiar with what we call the pigeonhole principle. But if you have many more possible inputs than possible outputs, then you must have a collision. And if the function is random-like, you will have many possible inputs that give each possible output value. So when we call it one way, it means that it should be practically hard to find an input. But if you have infinitely many time, if you have until the end of times, until the sun burns out, and you keep trying messages again and again every nanoseconds, then at some point you will get lucky. But what we just want as cryptographers is that it should be practically hard. Even if you have billions of dollars worth of budget and thousands of years, it should be impossible to find what we call a preimage. So preimage is an inverse of the function. So like randomness, we have these hash functions everywhere. That's why we also call it the Swiss Army knife of crypto. You find hash functions in signatures, in encryption, in what we call key derivation functions, whereby we derive keys from stuff like passwords, in file integrity checks, in MACs, so message authentication code, in zero knowledge proofs, in random generator, so everywhere. So then again, there's a difference between cryptographic hash functions and non-cryptographic ones. And guess what? The cryptographic ones are secure, and the non-cryptographic ones are not secure and possibly fast. But today, as we have, let's say, more computing power, there's little difference in terms of speed between crypto and non-crypto hash functions. The only cases where it matters is if you do, for example, hardware system with very low latency, very extreme constraints in terms of compute time. But if you look at the functions Blake 2 or Blake 3, we're talking of gigabits per second. So it's usually fast enough for most applications.
Hey, JP, sorry to interrupt.
Sure.
There's been some questions in the Discord about the slides. Do you by any chance have a copy of your slide decks available for the students to download?
They're not public, but at this point, but I can probably share the slides via Ring0 on whatever platform you guys have.
Okay, so we'll share the slides afterwards then.
Yeah. Cool.
Okay, great. Thank you. Sorry to interrupt.
No problem. I don't see Discord, so if you have any questions, feel free to interrupt me.
Okay.
Yeah. So now, what might seem weird to you at this point is that I talked about randomness, hash functions, but I didn't talk about encryption. I didn't talk about keys or secrets. Now we'll see the first situation where we have a secret key. And surprisingly, it's not for encrypting stuff. It's for hashing. And it's what we call a pseudo-random function, or PRF. And you might wonder why we just put a key in a hash function. So here, the idea is to simulate different hash functions. You might have hash function 1, 2, 3, 4, 5, but you don't want to have to design and implement and test all these different hash functions. You want only one. So here the trick is just to use this key as an index to simulate different hash functions. All these functions will behave completely differently because the key is different. And it will behave pseudo-randomly if you don't know the key. And if you know the message, it's impossible to predict what the output will be. So in this context, we usually call the output the tag. The name varies, but it's just to distinguish it from the output of a hash function that has no key. So it's often used as a kind of authenticator. So let's say I share a key. So I have a key, you have another copy of the key, and we're the only two people having this key. And I send you some message. I don't really care about the secrecy. There's nothing, incriminating, nothing secret. But I want to make sure that the message has not been modified. I want to preserve the integrity of the message. So I will compute a hash with a key over this message, like you see on this picture, and I will send you the message and the tag. And what you're going to do is do exactly the same. You know the key. You're going to recompute the output from the message and the key. And if you obtain the same output, the same tag, then you will think that, okay, that's what JP computed, because nobody else could have done it. Because without the secret key, you cannot determine the tag of a given message. You can see it as a kind of signature, except that it's not what we call signature in crypto. So again, that's what we see it as a family of hash functions. That's how it's described in theoretical books. There's something that is called HMAC. So MAC is nothing to do with Apple. It's message authentication code. So it's what I described just before, this kind of signature, but we don't call it signature, we call it a MAC. And if you just have a hash function, a normal hash function, that is not designed to use a key, but is just designed to take a message. So this construction called HMAC for hash-based MAC is just a way to turn any hash function into a hash function with a key. And as you can see, there's two invocations of the hash function and two keys, two subkeys. So the way it's designed is not the simplest possible ever, but it's secure. I mean, it's okay to use it. It's also a standard, but today there are some better options. For example, if you look at the standard SHA-3 or Blake2, you don't need to bother with HMAC. The hash function directly gives you, let's say, a slot for the key, so to speak. You can directly use it with a key, where the key is a special argument. Okay. So to complete this part, I will briefly talk of something that we call pseudo-random permutations, or PRPs. And it's like we've seen before, like pseudo-random functions, but with a small twist. The difference is that the output has exactly the same size as the input, and also that you can invert the function if you know the key. So it's a permutation. For each possible input, there's only one possible output and the other way. So there's another name for these functions. It's also called block ciphers. So a cipher where you encrypt a block. So as you can see, it's very similar to what we saw before to the PRF. There's a message, there's a key, and there's an output. So here the output is a ciphertext. And you can do the inverse operation. You can decrypt, because if you can only encrypt and not decrypting, then your cipher is pretty useless. So if you know the key and you know ciphertext, then you get back the message. So what does it mean for a cipher like this to be secure? So it means that the message is secret, okay. But secret given what? Given just the ciphertext? Given many ciphertext? Is it secret if you know the key? No, of course not. So if you know the key, you can decrypt. So the assumptions we do when we design ciphers is that we assume that even if you know many messages and many encryptions of these messages, so many pairs M, and C, then it should be impossible to recover the key.
Hey, so JP, sorry to interrupt again,
sure.
But I just wanted to check. Are you currently sharing your slides?
Yeah, if people want the slides, I'm happy to share.
No, but I mean, right now, are you currently sharing?
Right now.
Slide screen.
Well, as I'm presenting, I cannot, upload them at the same time. But
no, I mean, are you showing them on the video? Because
yes,
I can't see them, and I'm getting a few questions from people who can't see them either.
Oh,
so I think the screen sharing has not worked correctly.
The screen sharing is dead. Yes, well, it just disappeared. Okay, now is it back?
Yes, now it's back. Thank you.
How long have I been talking without using the slides? Okay, hopefully not.
5 minutes-ish.
Ready? Oh, sorry. Should have told me. Now you can see the slides.
Yes, now we can see the slides.
Yeah. So that's what you missed.
Yes, I'm so sorry I didn't mention it before. I thought you were not sharing on purpose.
No, I always have slides. Okay, so sorry guys. Now you can see the slides. Hopefully,
so thank you, folks, in the questions and on Discord for notifying us of this.
Yeah. So here's what's block ciphers, PRP, PRF, and then hash functions. And okay. So let me go back to block ciphers. Okay. So then again, we have the good and the bad. The bad is the old stuff from the 60s, and the bad is also what you would design yourself. Because when I started crypto, there were a lot of people doing their own ciphers, but it's not because you cannot break it that other people cannot break it. Most of the time, I would say 95% of the cases, you would just go with the AES cipher, which is the single biggest standard. Some case where you don't use AES is some governments, some countries that don't want to use a US standard, such as China, Russia, and they have their own crypto. But it doesn't mean that AES is backdoor. That's just mean they have whatever reasons they have, but you don't need to worry if you use AES. What you may want to worry about is the implementation you use, because there's more bugs in the code than in the specifications. Now, finish this part with the mods, because what I showed you is how to encrypt a block. So a block like this one, and the block is usually pretty short. It's 16 bytes, 128 bits. And what can you do with that? You want to encrypt, any message of any size. But if you do it the native way, you get the following problem. So let's say you encrypt this plain text, this message in blue. You learn when you listen, and you obtain the ciphertext in green. But there's a little problem here. Let's look at the green stuff. You see the first block, you see the fourth block, X, D, Z, B. Oh, they're the same. So let's say you have no idea what the plaintext is, but you just see the green message, you just see the ciphertext. So even if you don't know what is encrypted, the ciphertext gives you some information. It gives you the information that the first block is identical to the fourth block. And we consider that it is a leak of data and that it compromises the security of the cipher, of the encryption scheme, because you should not be able to determine any piece of information on the content of the message apart from its size. And that's why people say, yeah, this mode called ECB is insecure because you can see the penguin. So of course it works with many other types of animals, but historically Tux has been used for this. So the solution is to use the blockchaining mode, so nothing to do with blockchains. It was here even before blockchains. CBC mode, it's super simple. You encrypt the first block and you take the output and you do an XOR between the output of the first block and the input of the second block. And then you encrypt it again and so on and so forth. And you see the first output and the fourth output, they are now different. So it doesn't leak the information we had in the previous case. The only problem is the first block, because there's a first block and there's no block before it. So we have to simulate a virtual block. So that's what we call the IV, initial value or initial vector. It's a value that should be random, that should be different for each time you encrypt a new message. There's another case of encrypting with a block cipher, but which is pretty weird. Actually, you don't encrypt. You use the block cipher to generate a random string of bytes. So the orange part, the key stream. So you encrypt, so to speak, value n that we call the nonce, concatenated with 1, then with 2, then with 3, and so on and so forth. So the output of each block is different. And then you do an XOR between your message block and your keystream block. And the idea is that the orange stuff will be unpredictable and random. So if you XOR it with some message, then the output will be random as well. So of course, you want each of these orange blocks to be different across one message and different across messages. However, if you reuse the same n value, the same nonce across multiple messages, you will get the same orange blocks. And that's a problem. The problem is the following. So let's say you encrypt two messages, P1 and P2, for plaintext1 and plaintext2, respectively into ciphertext1 C1 and ciphertext2 C2. Now you have P1 that is equal C1 XOR with the keystream S, and likewise P2 equals C2 XOR S. So if you look at the first equation, you can say that S equals C1 XOR P1, which means that if you know C1 and you know P1 and C2, and your goal is to determine the plaintext P2, it is trivial to compute it by combining C2, C1, and P1. So you can decrypt essentially for free. That's why you need different nonces. And there's been many problems, many real-world problems. It's just one example from 2011. So it was a cloud backup system. So even before the word cloud was being used, what you see here is the patch of part of the code. So the patch syntax, the first two lines with the minus sign means that these two lines have been removed in the new version, and the lines with the plus sign have been added. So maybe you can spot the problem that was introduced by this patch. It's calling the function AESCTR, which is the one we just saw, AES counter. And in the line removed, we have a nonce plus plus. So plus plus means that the nonce has been incremented, meaning that it has changed its value, and the next time it will be another one. So if you have a nonce equal 1, you do plus plus, then you obtain a nonce equal to the next time. However, if you look at the 1, 2, 3, 4th line of code, excluding the comment, if the plus plus has disappeared. Why? Well, because they forgot it. And the problem is now that they were reusing the same nonce for every single message. So just 2 characters missing and a complete security disaster. So that's why I don't really like this mod, because of its fragility. You just forget 2 characters and then boom, everything is broken. So there was a very honest and clear advisory where they explained the problem, how it happened, and what it could have caused. So yeah, that was sad. But that was 2011. You might say, oh, now people have learned from it. Last year, I did a code review of some blockchain wallet system, and there was exactly the same bug. So there we have this disadvantage, this very fragile property, that if you reuse the same nonce, then the cipher is broken. However, it's pretty fast in software because you don't even need to know the message before computing the encryption stuff. And also the size of the ciphertext will be exactly the size of the plain text. And so you just need the encryption function, not the decryption. So another type of encryption, which I will not cover today, but I have in the full version of the deck, is authenticated encryption, whereby you produce not only a ciphertext, but also a tag. So you encrypt and authenticate at the same time. Now, let me move to the next presentation. I see that we have little time left. I will talk about public key encryption, but this is maybe the most complex, most mathematical topic of our whole training. So I'm not going to give all the details, just an overview. And I also eliminated some slides from the presentation. So I just want to give you a flavor of what it's about, to give you the main ideas, but I will not go into all the details. So if you had an overview already. So public key, it's completely different from what we just saw. Maybe the only thing in common is that it's using computers, and that the goal is to, protect confidentiality and integrity of data. But it's based on math. On math. I don't know how to call it differently. More specifically on number theory and on complexity theory. And we have this concept of hard problems, because when we talk of a problem in math, in complexity theory, it's something very well defined. It's not like, oh, shit, I don't know how to solve this equation. I have a problem. No, it's a problem where you have an equation and you have to solve the equation for a very well defined meaning of solve. So if you take the first one here, integer factorization, the problem is extremely simple. I could explain it to my 11-year-old daughter. So you have a number n, which is equal to p times q, where p times q is a big number, and p and q are prime numbers. So numbers that can only be divided by themselves and 1. So it's easy to do a multiplication. Even if you have big numbers, it's pretty fast. But the opposite, you don't know p, you don't know q, you only know n. You know that p and q exist, but you want to find them. Well, how do? You try all possible numbers, but when there's an exponential number of numbers, then you just can't do it. There's way too many numbers. And we don't know how to do it with the computers we have. We know how to do it with the computers we don't have, but we don't have them. That's the quantum computers. The second equation is underneath the discrete logarithm problem. So you have h equal j to the power of x in some specific mass structure. You know h, you know j, and the goal is to find x. It's like, oh, I know 2 numbers, I just need to find the third one. But this is about as hard as the first one, and that's practically hard. And we have good reason to believe that they're hard. And they better be hard because all the security of internet relies on these 2 problems. the connection to every HTTPS website, TLS, your not your mobile phone cellular connection, but your WhatsApp messages, your Signal messages, not Telegram because it's not encrypted. Yeah, SSH, everything is relying on these two problems. So RSA is the first one. It comes from the late 70s. That's the math details, but I will skip the explanations, but just go to the last line to show you how simple it is, at least on the face of it. You have a number x and you raise it to the power of e. So x is, I don't want to say your message, but it's the data that you give to the function. E is a public parameter. And the game is that to invert this function, you need to know a secret that we call the trapdoor. And this trapdoor will allow you to invert the operation. And we make it in such a way that inverting corresponds to decrypting. There's another completely different type of encryption, type of public key technique, which is elliptic curves. The name is a bit a misnomer because they are only curves insofar as you use the right mathematical group. So on the top right, you see something that arguably looks like a curve. But on the bottom right, it looks like a cloud of points. Doesn't really look like what we feel would be a curve. But that's actually the curve we use in crypto, the one on the bottom right. So it's a bunch of numbers on a plane of 2 dimensions defined by some equation with some specific form of which you can see examples on the left. And we use these elliptic curves, this cloud of points, to do cryptography based on the hardness of the problem of the DL, discrete logarithm problem. But then you might say, what do you mean? There's no addition, there's no multiplication. Well, we have a way to construct an addition of points and a multiplication of points, which is quite different from the natural addition we're used to, but it behaves like addition and multiplication. So why do we use these crazy complex elliptic curves? It's because they're often more efficient and their key is much shorter. Here you have an overview of the security level compared to the key size. And as you can see, sorry, you can get, for a given key size, then the security level grows much faster for the elliptic curve than for RSA. So if you have a key of, let's say, 512 bits in the middle of the x-axis, then with RSA, you get only 64 bits of security. Whereas with elliptic curves, you get 256 bits of security. So you go from insecure to secure. So now how do we encrypt stuff? The main difference in asymmetric public key crypto is that you have 2 keys. It's not a shared key. It's a secret key and a public key. So the secret is, of course, secret, and the public is not necessarily secret. It can be kind of secret, but usually it's fine if it's not. So the goals are almost the same as the one we saw before, except that we added non-repudiation. And non-repudiation is when you issue a digital signature, you're the only one to know the secret key that allows you to sign. So no one else could have signed on your behalf. Whereas if you share a key with someone else and a message is signed, a signed message is somewhere, then either of the 2 parties have signed it, but you cannot say, oh, this person signed it, because at least 2 persons know the key. With public key, you have the secret key belongs to only one party. It's not shared, generally. So if you sign a message, it's a proof that you meaning the individual, the system, the company, that you signed it. That's what we call non-repudiation. So you don't have a way to say, I didn't sign it. So I want to just comment on this because it sounds pretty interesting. From a legal perspective, it means, you can go to a court and say, this person signed this message, so they're accountable for it. But occasionally I check the court records in the public archives of the US, and I don't think there's ever been a case where non-repudiation was used as a hard evidence to convict someone in court. So signatures have been used as one piece of soft evidence among many others, just logs, messages, and screenshots and whatnot. But I don't think someone has ever been convicted just because they use digital signatures. So there's crypto, there's math, and there's reality, which is more complex. So yeah, public key, private key, and of course you can compute the public key from the private key or secret key. We use both terms. But of course, you cannot do the opposite. You cannot compute the private key from the public key, because otherwise it would not be private in the first place. So you see, we have again this concept of one-way function of permutation. You go one way, it's easy, and the other way, it's hard. And we define encryption as public key encryption in quite formal ways that I try to simplify here. But first, you have to have a key in the first place. So that's why we use key generation systems. So instead of getting one single key, you get two keys, the secret and the public one. When you encrypt, use the public key. So I encrypt to a friend. I know their public key. I will encrypt. And once the message is encrypted, I cannot decrypt it. Only them can decrypt it because they know the secret key. Okay. That's the case of RSA encryption. I'll skip it just for the sake of time. If you do it in the simplest way, it's completely insecure because there's many attacks. And you have to use something like this called RSA OAEP, optimal asymmetric encryption padding, which looks completely over-engineered and complex, and you're completely right. And it was proven secure. It's designed in such a crazy way for several reasons, one of which is we wanted to have some proof, some mathematical proof that it was secure for some definition of security. And that's why we ended up with this. You can see the small circles G and H in red. So these are hash functions of a specific type. So we see use hash function to encrypt, and the yellow part on the top right are, so it's a random value. So we also use random numbers, meaning that encryption will be randomized. If you encrypt twice the same message with this, you will get two different ciphertexts. So the idea is that looking at a ciphertext will not give you information on the message, because if you encrypt the same message multiple times, you know how the ciphertext would look. And since anyone can encrypt with a public key, then you could test if the ciphertext is the same as another ciphertext. So it would leak information on the message. So Elgamal is another type of encryption, which is not using RSA, which is not using factorization, but is cryptologarithm. And it's quite similar to what we do with elliptic curves. So there are other constructions, something called Kramer-Schub that you never heard of, probably because nobody is using it, but cryptographers love it because it has very nice properties in terms of security. And Paillet, which wasn't used anywhere until a few years ago, where its property of being homomorphic was used in what we call multi-party computation, and specifically threshold signature. So again, we always combine different crypto primitives with each other. So this Paillet encryption scheme was used in multi-party signature systems because of its property of homomorphism. What this means is if you have two ciphertexts, so you see the equation here, encryption PKM1 and M2, and if you multiply the two ciphertexts, then you obtain another ciphertext, but a ciphertext that would decrypt to M1 plus M2. So we kind of transform multiplication into addition, which is pretty cool and has some cool applications. Now let me move to signatures. So again, you need keys, public key, private key. You sign with a private key, and you verify signature with a public key. What's important to know here is not just the opposite of encryption. It's not, oh, it's just, encrypting with the secret key and decrypting with the public key. A signature is fundamentally different from encryption. The security goals are different. It's not about confidentiality, it's about integrity. And that's why we use different constructions. Then again, you can use RSA directly, and you can use in plenty of stupid ways, and you can also use in less stupid ways. So again, we have this crazy construction from the 90s called PSS, probabilistic signature scheme, which is probabilistic, which means randomized. And again, you see hash functions, you see an input called the salt. It's using randomness at some place. So quite complex, but somehow for a reason. And then ECDSA, the elliptic curve digital signature algorithm, which is a standard. So again, we do some arithmetic operations, and it's what is used today in, I would say, most of the mainstream applications of signatures, and in particular in the blockchain systems. So Bitcoin, Ethereum, and many others are using ECDSA, even if they're now moving to some different things. But ECDSA is almost everywhere. And it has something in common with AES-CTR. What it has in common with AES-CTR is its fragility. If you look at a signature bullet and sub-bullets here, you have to choose a random integer k, and then you do some stuff with this k. You invert it and you multiply it with other values. What if this k is not random? What if you reuse the same k twice? So if inadvertently, or if you have a bad PRNG, if you sign twice with the same k, different messages, then it's game over, because someone can directly recover your secret key just by doing simple operations with the signatures. And that's discussed here. There's some workarounds, and it's been famously exploited in 2010. That feels like it was yesterday. To hack the PS3, the PlayStation 3 gaming console. So Sony had some kind of, mechanism whereby they would sign the games using their key, and the console would verify the signature and only authorize the games signed by Sony to run on the console. And it would be done in some kind of secure environment. And the goal was to prevent people from running arbitrary programs on the PlayStation 3. So, okay, it was using ECDSA, standard algorithm, good elliptic curve, everything standard, good key size, and so on. The implementation was okay, except that the random value was not random. So when people noticed it by reverse engineering the code, they just took two signatures and computed a private key, and then they could run whatever program they wanted on the console, which was pretty cool again. So now for the last part of this slide, the key exchange, which is maybe the single most important public key operation we use today. Because when you do a TLS connection, when you do SSH, you do a Diffie-Hellman key exchange in some way. And here's, again, some kind of magic. You have a public key and a private key. So here you have Summer on the left and Rick on the right. Summer, she picks a value A. So G is what we call a generator. It's a parameter that is not really secret. So she does G to the power of A, and Rick does the same. He picks a B, he sends G to the power of B. And Summer computes the value she received. She raises it to the power of A. She obtains G to the power of AB, and Rick does something similar. And you also get G power to the power of AB. Now, if you observe the values exchange, it doesn't allow you to determine G to the power AB. You know G to the power of A and G to the power of B. But because of the properties of what we call Diffie-Hellman, you cannot determine G to the power of A times B. And that's again some crypto magic, except that it's not perfect if you're a person in the middle, like if you have our friend a bird person. What he can do is modify the value received and pretend to be the other party. That's what we call a man in the middle, or a bird in the middle in this case. So we have some workarounds to deal with this. It's called authenticated Diffie-Hellman. So you see more keys. Many problems in life, well, not in life, but many problems in engineering, in security can be solved using cryptography. And in turn, many problems in cryptography can be solved by adding more keys. So that's why we say that cryptography is just a way to turn any problem into a key management problem, because then you have to worry about how do I generate the keys? How do I communicate my public key to the other parties? How do I do backups of my keys? What happens if I lose my key? What we call key lifecycle in the enterprise setting. Okay, so with the time left, I think what's best is that I talk about quantum computing and post-quantum crypto. Maybe ZK proofs is too ambitious. And quantum stuff is also more fun. So I hope you can still see my slides. Yes, post-quantum.
Slides are visible, yeah.
Yeah, the slides, cool. So that's what you need to know. It's basic quantum physics equations, what you have on the first 2 pages of a book about quantum mechanics, the Schrödinger equations, which describes the evolution of a quantum system, the Hamiltonian, so that's very basic. So the idea of quantum computers has nothing to do with crypto initially. It just has to do with physics. So Richard Feynman, one of the most famous physicists of the 20th century, he wanted to understand nature, so physics, and he wanted to simulate how a microscopic system evolves over time using computers. And he pretty quickly realized that it was not easy because there were too many variables, too many numbers to keep track of. And you see the question here, can quantum systems be probabilistically simulated by a classical computer? So quantum system, if you don't know quantum mechanics, it's essentially it's our theory of how we think particle behaves at the subatomic level. And there's a lot of randomness involved. And as a randomness, not in the sense of, oh, we don't know everything, there's too many equations to compute, so we cannot predict it practically. No, randomness in the pure absolute sense. So like crypto, quantum mechanics is like completely counterintuitive and magic. So if you just look at the line -4 here, the answer is certainly no, you cannot simulate nature with a classical computer. Classical computer is, like electronic circuits, like the computers you have at home, the mobile phone you're using to watch this talk. We need something different. So if you want to fight fire with fire, so you need something that behaves like nature. To simulate quantum mechanics, you need quantum mechanics in the first place. You want something that obeys the rules of quantum mechanics, and that was the idea of a quantum computer. So the idea is completely crazy again. Normally in a computer, you have bits, 0 or 1. So you look at it, it's 0 or it's 1. With quantum systems, we have quantum bits or qubits. And the qubit, it's 0 and 1 at the same time, so to speak. It's what we call superposition. So you have an object, you have this quantum bit, which is made of subatomic particles. It can be simulated with photons, ions, or whatever setup. And it's in some undefined value. It's not a value that we don't know, but exists. It's a value that doesn't exist yet until you observe it, until you measure it to ask, are you 0 or 1? And once you measure it, it's 0 or it's 1 forever with some probability that we can determine based on the amplitude, which is a property of the quantum state. So you can see the amplitude as a kind of weird probability. So in math, probability is a number between 0 and 1. So 0, you have no chance at all. 1, it's a sure thing. In the quantum realm, the amplitude can be negative and can also be a complex number. So of the form a plus bi, where I is the imaginary unit. So again, it's really counterintuitive, but that's something that really describes correctly how the world behaves. So we have the superposition state, and we can define quantum bits, we can define quantum bytes. So quantum byte is an object that can be in one of 256 possible values. You can define quantum states of arbitrary size, and you can make this state evolve. So you can create what we call a quantum circuit. So a series of transformations, and at the end, you have a different state, a different quantum state, and you observe it, and that's your result. That's what we have here. I don't want to say it's simple because it's not, but it can be simulated in simple terms. If you have, let's say, a number n of qubits, then you have 2 to the power of n possible combinations. So if you have 2 bits, you have 4 possible values. If you have 10 bits, you have 1024 possible values, and so on. So you would have to keep track of all the possible probabilities of all these possible values if you were using classical computer. But with a quantum computer, you just need 1 bit to 1 thing for each of these qubits. You don't need to keep track of all the probabilities that I mentioned before. It just happens. So that's what you cannot simulate it with a classical computer. You cannot simulate it practically. You have too many variables to keep track of, at least once the system gets big enough. If you have maybe more than 50 qubits, then it's not practical to compute. You will need way too much memory, way too much time. But if you were to simulate it with way fewer qubits, it obeys very simple rules. It's like linear algebra that we learned at school in high school. So matrix multiplication, vector matrix multiplication, so just basic additions and multiplications. So if you have a circuit like the one you see here, then each of these cells, the green, the blue, the red stuff, they can be described in terms of multiply a vector by a matrix or multiply a matrix by a matrix, where the matrix has a given property. And at the end, you observe the qubits, and that's the solution, or that's the output value of your quantum program. So that looks simple, but making this work in the real world is extremely hard. And I'm here today to talk about this because of what we call quantum speedup. Because there's some stuff that you can do practically with a quantum computer, at least in theory, which you could never do with a classical one. So it's not because we don't know, it's not because we haven't tried it hard enough. It's because fundamentally, mathematically, we know for sure that it's a fact. So we have what we call a super polynomial quantum speedup that you can see as some exponential boost, but it's not in terms of speed as in going faster. It's in terms of doing way fewer operations. So it's not in terms of, the frequency is much higher in terms of operations per second. So it's just a completely different computation paradigm. So another thing that is usually poorly understood is the concept of quantum parallelism. So I told you that a qubit is multiple values at the same time. It's, so to speak, simplified. So it's tempting to think, oh, that's great. So I can try all the passwords at the same time. I can try all the keys at the same time and just pick the one that works at the end. Well, it's much more subtle and complex than this, and you cannot do what I described. You cannot brute force all the possible values in superposition and pick the best, because it's not how quantum computing works. So very quickly, another point is that quantum computers cannot solve any problem faster, especially what we call NP-complete problems. So that's the class of problems that are exponentially hard to solve. They are the constraint satisfaction problem. Let's say the scheduling problems, maybe, the SAT problem, the traveling salesman, all these problems that we find in many applications, maybe, integrated circuit design, in train scheduling, even in video games, in Tetris and whatnot. Tetris was proven NP-complete, NP-hard, I think. So we can characterize the problems that quantum computers could solve efficiently and more efficiently than classical ones, but they don't include all these hard problems. But the good thing is that some crypto problems are in BQP, the bounded error quantum polynomial time, which is the class of problems where quantum computers are very useful or would be very useful. Last thing I want to clarify is quantum supremacy. Maybe you've read the news last few years and read that some company achieved quantum supremacy. So it doesn't mean that you will have quantum everywhere in every machine, that quantum solved all the hard problems. It just means that we have built something that kind of works like a quantum computer and that managed to do something that we would not be able to do with a classical computer. But this something doesn't have to be meaningful or useful for that matter, or it doesn't have to have anything to do with crypto. Just do something, do some computational task that could not be done with classical computer. And what has been done so far in that space has been very specific and very contrived and completely useless as far as the applications are concerned. So if you want to learn more about this, I really recommend this book by Scott Aumasson, very funny, touching on many topics. And now we'll go back to crypto. So the impact on crypto is potentially disastrous, because I showed you these equations before. So the factoring problem, the discrete logarithm, and these two problems would be completely destroyed if we had a quantum computer. That's why people worry a bit about it, and that's why there's a lot of, or that's partially why there's a lot of funding and hype in that space. So it would be faster really in the sense that we would go from millions of years to, I don't know, millions of seconds. So how bad would it be depending on which type of crypto you use? For signatures, it's not too bad because, let's say, at some point you learn that a quantum computer could break your signatures. Well, you can just issue a new signature with an algorithm that is post-quantum, which is immune to quantum computers. For key agreements like Diffie-Hellman, well, it's a bit worse, because if someone observed and captured all your communications in the past, let's say you use WhatsApp, for example, and someone kept a copy of all the messages you exchanged, and from the very beginning to the very end, then they would be able to decrypt it, but they have to have stored it in the first place. For the pure encryption, it's the worst, because if you create a ciphertext and the ciphertext is out there and someone kept a copy of it, then in 10, 50, 200 years, they could decrypt it. So you don't have to worry too much about signature as much as you do for encryption. Now, the good news is that we're very far from a useful quantum computer. So not the logarithmic scale here is 1, 10, 100, 1,000, and so on. In the quantum computers we have today, we have between 100 and 1,000 qubits, which are stable, which are usable for a very, very short time. We're talking not even milliseconds. What we hope to have in the next 5 years or so is, reach 1,000 or a bit more 1,000 useful qubits. But to break crypto, we would need 1 million qubits, many more. So I don't have time to explain the details, but that's a fact. Yeah. So the scale scenario looks like this. There's some marketing by IBM, some marketing by D-Wave, which is not doing a quantum computer, but they say they do. There's some research papers that describe in details how many qubits you will need. Several papers, more recent one. Some papers whose title is a bit misleading. Say, oh, only 13,000 qubits? When I read this, I almost fell off my chair. But the catch here is that you need 430 million of quote-unquote memory qubits. So there's no shortcut, it seems, to these millions of qubits. The good news is that it only affects public key crypto, RSA, discrete log, FT curves, and not AES, not symmetric crypto. There's something called the Grover algorithm, which gets you some small speed up. So you go from 200 to 128 to 264, in theory at least. But even if you worry about this, you can just double the key size and you retain the same security level. And there are some papers that show that even then, such a machine would be ridiculously big and costly and slow to break real ciphers in the real world. And the very last part, I have like 5 minutes left, is to give you a taste of what we call post-quantum or quantum safe, quantum resilient crypto. So it's the algorithm that would not be broken by quantum computers. So they don't have to rely, they must not rely on RSA or discrete logarithm or elliptic curves. They must use something different. And even if you don't believe that quantum computers should come, you can just see it as an assurance, like a low probability, high impact potential risk that you may want to address in your risk management policy. So the US government talked about it, not because they have anything secret that they are hiding from us. It's not in that space. It's just because they work in the public sector, and you know that deploying stuff in the public sector, especially in the US administration, takes a lot of time. So they just, want to be sure in case there's a big breakthrough in quantum computing, they will be ready. So it took the form of a public project, a public competition, where academic researchers published and submitted algorithms of different types. You have very diverse constructions, some of which date back from the 70s, and some candidates, some standards, or some ciphers that may become standards are almost identical to designs from the 70s. So this is what we call lattice-based crypto. Don't have time to detail, but that might be the most promising in terms of encryption and also in terms of signature. And hash-based is where you only use hash functions to create signatures, which makes no sense at all, which looks very stupid, but nonetheless, it works. And NIST, the US agency in charge of doing the technology standards, a few months ago, they picked a hash-based signature scheme as a standard called Sphinx Plus. Here, I go and try to explain the underlying ideas. In terms of performance, it's sometimes slower, but not necessarily slower than the crypto we use today. So here we have a comparison between ECDH, elliptic curves, and some types of post-quantum crypto. So as you can see, the purple one is, interestingly, quite faster. Kyber is even faster than elliptic curves for, encryption, decryption. Likewise, for signatures, we have some pretty good numbers. And if you want to switch to post-quantum crypto today, there's a number of options. The standards are coming. NIST already announced some of the standards. They have not published the specification. It will take at least one or 2 years. But you have a number of software libraries that offer post-quantum crypto in AWS, the KMS, key management system. You have the option to use post-quantum TLS link. And the big companies like Apple, Google, Cloudflare, they're also working on it and are deploying post-quantum crypto. Maybe they've done it already. So that's it. I will stop sharing. So thank you for your attention. I hope it was useful. You learned things about crypto. And you're welcome to join the training, to send me questions. You can go to my webpage. You will find my email. You can find me on Twitter as well. And thanks again to the Ring Zero people and Samuel.
Thank you, JP. Yeah. Thank you for a lovely workshop. Yeah. Thanks for joining us once again on this edition of Return to Workshops. So folks, with this, all our 3 workshops are done. We will be sending out an email and some tweets about when the workshop videos are going to be published. So please subscribe to our social media channels on LinkedIn, Twitter, Mastodon, Facebook, and Instagram, whatever your choice may be. Second, the early bird sale for Return to Exploit is still on. The early bird discounts will be lasting until the 31st of December. So we have another 10 days. If you folks wish to participate in JP's training or any other training, I would suggest please make good use of the discounts. Please tell your friends or colleagues as well about the discounts. And last but not least, I wish you folks a very warm, happy, enjoyable holiday season. Thank you very much. We will see you again next year. Take care.
Thanks, Emil. Thank you, guys. Bye.
Thanks, JV. Thank you.
Bye.
Bye.